Pre-calculus again. Okay. Sum and difference for sine and cosine. Motivating question. We can find 90 degrees on the unit circle, but if we couldn't, let's say we wanted to find cosine of 90 degrees and it wasn't on the unit circle. 90 degrees is the same as 60 plus 30. So is cosine of 90 the same as cosine of 60 plus cosine of 30? Cosine of 90 degrees, and you can get this by looking in your calculator or looking at the unit circle, cosine of 90 degrees should be 0. But if you do cosine of 60 plus cosine of 30, then what you get based on the unit circle is 1 plus the square root of 3 over 2. If you do it in your calculator, you get something like 1.37, whatever it is, it's not 0. So cosine of 30 degrees plus 60 degrees is not the same as cosine of 30 plus cosine of 60. So you cannot just add two things to get, let's see, you can't add two cosines. You can't add the cosine of two different angles to get the cosine of the sum of those angles. What you have to do instead is use a formula. Now, there's a pretty long proof for this in the book. Well, it's not that long. It uses first the law of cosines and then the distance formula and finds the formula for the for the difference of cosines. That is the cosine of the difference of two angles. And you get, if you plug in negative beta instead of beta, you get the formula for the sum. Here is the formula. So I'm happy to work through the proof with you, but I think most of you would rather just have the formula. So here's the formula. Cosine of alpha plus or minus beta. Alpha and beta are just variables. They're just like x and y, but they describe angles. Plus or minus means the formulas for the sum and for the difference are so similar that I'm going to write it as one thing. So cosine of alpha plus or minus beta is equal to cosine of alpha times cosine of beta minus or plus sine alpha times sine of beta. And this minus or plus business, this just means they're opposite. So this is how this works. We know that this should be 0. So let's try this formula and see if it does give us the right value. So 60 degrees is my alpha, 30 degrees is my beta. Using my formula, this becomes cosine of 60 degrees times cosine of 30 degrees. That's a plus. That means I'm going to use a minus. That's what I mean when I say these are opposite. If there's a plus here, we use minus in here. Minus sine of 60 degrees times sine of 30 degrees. Now, based on my unit circle, the cosine of 60 degrees is 1/2. The cosine of 30 degrees is the square root of 3 over 2. Sine of 60 degrees is square root of 3 over 2, and sine of 30 degrees is 1/2. So if I multiply this, I get 1 times square root of 3 over 2 times 2 is 4, minus square root of 3 over 4 equals 0. So this formula does give us the right value for cosine of 90 degrees. Where this comes in handy is when we need to find exact values. That is, I don't want the calculator approximation. I want the exact value. Even if that means I have simplified radicals and fractions, I want the exact value for the cosine of some angles that are not on the unit circle. So long as we can use addition or subtraction with angles that are on the unit circle. For this one, I'm going to use 30 plus 45. 30 degrees and 45 degrees are both on the unit circle, so I can get their values from there. They add up to 75. This is not the only option. We could also use 120 minus 45, or maybe, 135 minus 60, or a bunch of other things. They all give you the same answer. So 30 degrees is my alpha, 45 is my beta. My formula is cosine 30 times cosine 45 minus sine 30 times sine 45 equals cosine of 30 degrees is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Sine of 30 is 1/2. Sine of 45 is square root 2 over 2. Now, you cannot add radicals, different radicals, but you can multiply and divide them. So square root of 3 times square root of 2 is square root of 6, and 2 times 2 is 4. 1 times the square root of 2 is the square root of 2, and 2 times 2 is 4. They have the same denominator, so I'm going to rewrite this as square root of 6 minus square root of 2 over 4. That's the answer. You can go ahead and check it in the calculator, plug in cosine of 75, plug in square root of 6 minus square root of 2, and divide by 4. You get the same value. But what you get from the calculator is the closest approximation that it can make. This is the actual answer. Now, if I used one of these other things, if I used, for example, 120 minus 45 instead, in case you're wondering, it would work like this. Cosine 120 is negative 1/2 times square root of 2 over 2. Sine of 120 is positive square root of 3 over 2, square root of 2 over 2. And I would get negative square root of 2 plus square root of 6 over 4, which is, as you can see, the same as that, just written in a slightly different way. So you can use any combination so long as adding or subtracting them gives you the value you want, and they're on the unit circle so you can look them up. Cosine 165. For this, I'm going to do cosine of, all right, let's do a difference. So cosine of 225 minus 60. We could also have used 135 plus 30. Cosine 225, cosine 60, plus, because remember we use the opposite, sine 225, sine 60. Cosine of 225 degrees is negative square root 2 over 2. You can look this up on your unit circle. Cosine of 60 degrees is 1/2. Plus, sine of 225 is also negative square root 2 over 2, and sine of 60 degrees is square root 3 over 2, giving us an answer of negative square root 2 minus square root 6 over 4. Cosine 555. If I'm going to do this, I need the coterminal angle first. So this is going to be the same as cosine of 195 degrees. To get 195, let's see, 135 plus 60 should work just fine. So this is cosine 135 plus 60, cos 135, cos 60. That's a plus, so I'll use a minus. Sine 135, sine 60. Cosine of 135 degrees is negative square root 2 over 2. Cosine of 60 is 1/2. Sine of 135 is positive square root 2 over 2. Sine 60 is square root 3 over 2. And now I've got negative square root 2 minus square root 6 all over 4. That's interesting. They all seem to be very, very similar. Oops. Nope, that's right. Sorry, just had a moment, had to check myself. They are going to be very, very similar. They will all come out basically to be some combination of square root of 6 and square root of 2 and 4. And the only differences will be whether the various things are positive or negative. That's okay. Don't worry about that. It's a little boring, but it's okay. But it means that what I'm going to be really looking for, to see if you got it right, is whether your positives and negatives are right. The next page is sine. Sine is very similar, but a little different. Excuse me. The proof of it is a little longer, but it's in the book if you want it. So here, the operation is the same. So, I'm going to do a couple of slightly different kinds of problems. Based on what we know about the period of sine, anytime you add 2 pi to a radian measure, you get the same value of sine. That is, sine has a period of 2 pi. So if you pick some place, some angle, and then you add 2 pi to it, you should get the exact same value for sine, because it should be repeating at that point. We're going to prove that algebraically by using the formula for the sum formula for sine to verify that sine of x plus 2x really comes out to be sine of x. So my alpha is x and my beta is 2 pi. I'm going to write sine of x cosine of 2 pi plus, we use the same operation, cosine of x sine of 2 pi. We don't know what x is. That means we don't know what sine of x is. So we can't substitute anything for it. That's fine. We leave it as is. Cosine of 2 pi, however, is 1. We don't know what cosine of x so we can't do anything with it, but sine of 2 pi is 0. Well, it doesn't matter what cosine of x is. If we're multiplying it by 0, it's still 0. So all we get out of this is sine of x, which means we have verified that if you add 2 pi to any angle, the sine value of the new angle is the same as sine value of the old angle. Similarly, the cosine of an angle is the same as sine of its complement. That is to say, sine of 30 degrees is the same as cosine of 60. Sine of 15 is the same as cosine of 75. Sine of half a degree is the cosine of 89.5. The complements work that way. So we're going to prove it. Sine of, let's see, here my alpha is 90, my beta is A, and I'm going to use minus instead of plus. Sine of 90 degrees, cosine of angle A, minus cosine of 90 degrees, sine of angle A. I don't know what A is, but I know that sine of 90 degrees is 1. So this is 1 times cosine of A, minus. Well, cosine of 90 degrees is 0. 0 times sine A will just be 0. All I get is cosine of A, and look at that. Sine of 90 minus A is the same as cosine of A. Using sum and difference identities, we can blah, blah, blah. You can read it for yourself, all right? I'm going to show you how it works. You need to use the formula, you don't need to know what x and y are, but you do need to know what both sine of x and sine of y are, and cosine of x and cosine of y. You could use the identities, the Pythagorean identities. You could also draw a right triangle like we did in Chapter 5. We are guaranteed to be in quadrant 1, so I don't need to worry about any negatives, so I'm just going to go with the triangle because it's quicker. If sine of x is 4/5, I'm going to draw a triangle, label my x, label my opposite 4, and my hypotenuse 5. You can use Pythagorean theorem to find the other side. The adjacent side is 3. So that means cosine of x will be 3/5. We're going to do this again for angle y. This is a separate triangle. Opposite is 5, hypotenuse is 13, and Pythagorean theorem or Pythagorean triples tells you the third side is 12. So cosine of y equals 12 over 13. Now, the formula is sine x times cosine y plus cosine x times sine y. And all we have to do is plug in. Sine of x is 4/5. That doesn't mean x is 4/5. We don't know what x is. Don't plug in for x. We don't know what x is, and we don't need to know what x is. What we're plugging in for is actually the entirety of sine. So we will replace sine of x with 4/5. There will be no words in the equation after this step. Cosine of y, over here, is 12/13. Plus, cosine of x is 3/5. Sine of y is 5/13. 48 over 65 plus 15 over 65 gives me 63 over 65. And that's my final answer. Again, there's no sine here and no cosine here anymore. This is the value of sine. It's a little like if I said square root of 100, you wouldn't say, oh, that's square root of 10. No, you would say, that's 10. Just don't repeat the sign, okay? All right. You'll notice these have the same denominator. That's always going to happen. Last one. Again, we're going to draw the triangle. 4 and 9. This one's not a Pythagorean triple. So we need to do a squared plus b squared equals c squared. a squared will be 81 minus 16, or 65. That means this missing side length is the square root of 65. That means cosine of angle x is the square root of 65 over 9. Similarly for y, 1 and 4, using the Pythagorean theorem, 16 minus 1 is 15. Missing side is square root of 15. Cosine of y is square root of 15 over 4. Sine x cosine y minus, because that says minus, cosine x sine y. Sine x is, there it is, 4/9. Cosine y is square root of 15 over 4. You could cancel out the 4. I prefer that you don't, for reasons I'll show you in a moment. Minus cosine x is square root of 65 over 9. Sine y is 1/4. That means we've got 4 square root of 15 minus square root of 65 all over 36. Now, if you canceled the fours here, you would get square root of 15 over 9 minus square root of 65 over 36. That's not wrong. These two things are exactly the same. They have the same values. I just prefer them to be written joined up in one fraction instead of as two. That's it.